All right, folks, getting into our last module here, Module 10, Reaction Dynamics. If you're following through with the Atkins textbook, this is largely derived from Focus 18. So we've got 12 learning goals to go through here, so that's why we're going to spend 2 weeks on this last module. And this first learning goal is on the mean free path and collision frequency, which we talked about at the beginning of the semester, but I wanted to bring that back so it's fresh in our minds. So recall here we've got the Maxwell-Boltzmann distribution of velocities that we derived previously. And if you recall, there's 3 different types of statistics we can get from this thing. The most probable, the mean, and the RMS. We're going to stick with the mean velocity for the following reasons. Because we're interested in collisions, the collisions of gas molecules and their rates of reaction, we want to use this mean velocity so that we can also rely on the mean orientation. That's what's going to give us the relative velocity. So now if we consider 3 different scenarios, one in which 2 gas particles are lined up like little soldiers here, they will have 0 relative velocity between the 2. If they are on a head-on collision and each one is traveling with velocity v, then their relative velocity will be 2 times that value. And now if we can imagine some overall average orientation, right, given by this 90-degree angle, then that will follow that their mean velocity is √2 times the velocity. So we're going to stick with that mean velocity right there. So recall here that we now have to use the reduced mass to describe this collision pair. And so that means if we're using the correct units, we want that to be in kilograms per molecule when using Boltzmann's constant. Okay? So that means in our reduced mass, each one of those is going to be the molar mass of the molecule expressed in kilograms per molecule. Now, of course, if we did this with gas constant R, then my reduced mass would be kilogram per mole. Either one of those would be okay. Okay, so now setting up how we get the mean free path, which is defined as the average distance a molecule travels between collisions, we want to put a molecule in this cylinder right here, described by distance lambda, and at the end of this cylinder is some molecule. So now if we put these on this grazing angle where they just barely collide, so by adding up their 2 radii here, that would give us the maximum possible distance that these things can exist between each other and still arrive at a successful collision. And so that area is given by pi d squared, or pi times the sum of the 2 molecular radii. And so here are some computed collisional cross sections, right? So that's the value of sigma, the collisional cross section. And so all of these are expressed in square nanometers. So you can see for things like nitrogen and oxygen, because those are very similar in size, their areas are roughly the same, the collisional areas. So this would be a collisional area between a nitrogen and a nitrogen, and a collisional area between an oxygen and an oxygen. In reality, if we think about the actual atmosphere, some of those collisions will be nitrogen-nitrogen, some will be oxygen and oxygen, and some will be nitrogen and oxygen collisions. So we'd have to come up with some average between 0.43 and 0.40 based on the 80-20 ratio of oxygen and nitrogen in the atmosphere. Okay. So, but it would all the same be very close to this 0.43, 0.40 nanometer squared. So now in deriving the mean free path, we'll start by noting that the mean free path is defined as the relative velocity between the 2 multiplied by the amount of time it takes for them to get there. So that is the distance. And now if we multiply all of that by the collisional area, sigma times C relative times delta V. That gives me the volume of my cylinder here, right? Area times the distance gives me a volume. And now if we want to think about our number density or concentration of this tube, we've got one molecule in there. So we place one of these just at the outside of the tube, and one molecule is inside of the tube. So that number density will be one molecule per unit volume, and that unit volume is sigma times C bar relative times delta T. Okay. So now if we think about how to compute what that volume actually will be, right, we can rely on the ideal gas equation, PV equals nRT, or I'm going to write this as PV equals big capital N times K Boltzmann T, where now recall little m is number of moles, big N is number of molecules. Okay, and of course we'd have to adjust the units of our volume appropriately for using K Boltzmann. All of the same, we'll rearrange this for number of molecules per unit volume, which equals P over K BT. We can then set P over KBT equal to this volume right here. We said one molecule per sigma times C bar relative times delta T. And if we rearrange that for how much time is spent between collisions, we can get the following. So delta T will equal, so do the algebra here, that becomes KBT over sigma times C bar relative times P. And then now if we collect some terms here, so I'm going to write, or just doing some little bit of algebra, instead of writing C bar relative, I'm just going to write root 2 times C, just changing C bar relative with C bar, times sigma times P. And so now 1 over that time will give me my frequency of collisions, right? So delta T is the time between collisions. If I take 1 over T, that gives me the frequency of collisions. And that's typically used, the letter Z is used to express that. And so all we've got to do is now flip that relationship. So we could write that as sigma times, and there's two different ways that we could write it. So I'll first write it here with the C bar relative. So C bar relative times P all over KBT. So we typically see this equation used to describe the collisional frequency. But now to get the right, to get the mean free path, what we typically do is just include that root 2. So now we've got a couple of different ways that we can write this. So just, there's several different ways we could do it algebraically. I'll just write that result directly, which ends up being the following. So we did say that lambda was C bar relative times delta T, and we've got an equation for that now, right? So that ends up becoming KBT, so plug in, right, the delta T equation for right here. And that ends up becoming KBT all over root 2 times sigma times pressure, right? And so we'll do some calculations with this in our live lecture so we can get a flavor for what these values actually are. Okay, I'll see you then.